Welcome back, Physics 30. This is the FM1.1 average velocity section. So in it, we'll be looking at distinguishing between distance and displacement, distinguishing between average speed and average velocity, looking at problems involving distance, displacement, and average speed and average velocity. So you would have encountered some of this in Science 10, in particular distance and speed. But we'll take a look at the difference here between distance and displacement and speed and velocity. So when you think of distance as being every step that you take when you're considering a movement without worrying about direction. And it is referred to as a scalar quantity. It just depends on how much it is, how big it is, what were those steps that you took. Whereas displacement is a change in position from some final point to some ending point. And it is a vector quantity, like we talked about earlier when we did the vectors section. So it depends upon not only a magnitude, but it also has a direction as well. So to kind of distinguish between those two with an example, if we considered a person walking 70 meters east, then 30 meters west, the total distance would be every step you take, right? So 70 and 30, it would be 100. But if we look at displacement, so if I started here and went 70, then 30, then stopped here, so if this is my finish, displacement is only looking at from starting position to finish position, so it would actually be 40. And the direction would be in the east direction, as you can see right there, because it's a vector. So again, distance, every step that's made. Displacement is just looking at the difference in initial and final positions with the direction. So if we looked over here, and if we looked at this scenario here, the distance traveled, if I start at the 10-meter spot and move to the 30-meter spot, and now here in this graph, I call it x1 and x2. I could have easily called it D1 and D2, and putting the half arrows to indicate that they are vectors. We can see what's happening. So the total steps that I took, just simply 20 meters. The change in displacement, now we don't necessarily need to do a subtraction because you can see we went 10, 20 in the positive x direction. So there's my direction right there. Direction, and then there's my magnitude. I went 20. But you could look at a change in position. So my final position was the plus 30. My initial position was the plus 10. So 30 minus 10, I get plus 20. Similarly over here, if I started at the 30-meter position and moved to the 10-meter position, well, in total, I moved 20 meters, right? Without a direction, we don't have to worry about it. But here, my D2 is going to be the plus 10 position. My D1 was the plus 30 position. So you can see here, 10 minus 30, I get negative 20. So again, it's telling me that I'm moving in the negative direction, and the amount I'm moving is 20 meters. So if we look at this page, there's one that we can try. An ant starts at a position of 20 centimeters on a piece of paper. That should be technically, I should put a positive there. So I'm just going to get you to insert a positive there. Turns around, goes to the negative 20-meter position. Well, we can imagine this on a number line. So 0, plus 10, plus 20, and then we have a negative 10 and a negative 20 position. I didn't do a good job in making them equally spaced, but that's all right. So we started here. So we could say D1, my position was at the plus 20. I move to the negative 20 position, turn around, and end up at the negative 10 position. So that's where I end up when all is said and done. And you can just look at this and see that it's going to be from start to finish, 10, 20, 30. You can see it's going to be negative 30. But we could put it in terms of final position minus initial position. We could do it like that. So delta D is my final position is at the negative 10. And my initial position was at plus 20. So as you can see here, we're going to get negative 10 and a negative 20 leading me to a result of negative 30 meters. The negative implies going that way and then 30. Then distance travel, all we need to do is just count all the steps. Count all steps taken. So we can go and see here 10, 20, 30, 40, 50. Or as what the cool kids say, 50. Well, I guess these are centimeters. They're not meter sticks, yeah, because that's quite a feat for an ant to go 30 meter sticks. So 50 centimeters every step that was taken. So it's that easy, ladies and gentlemen. Now we'll look at average speed. So speed is related to distance in that it's the total distance traveled over the time that was taken to do that movement. So we can see here average speed, distance divided by time, or in terms of a formula we could just write delta D over delta T. Change in distance or total distance is what this could represent, and the time taken to do that distance movement. And of course that depends just on size only. Whereas average velocity is related to displacement. So only looking at the difference between final position and initial position. So you can see these formulas look very similar with the exception of the half arrows indicating vector quantities. Okay, so speed deals with distance, velocity deals with displacement. So now we'll take a look at a couple of examples dealing with that. So example 1, during a 3-second time interval. So 3-second time, so that's going to be my time in all of these questions. The runner's position changed from the 50 meter position to the 30. So you could draw out this on a coordinate system here. We're going from the plus 50 down to the plus 30.5, and you can see we're going to be doing this. All right, so we're moving from 50 to 35. So if we're to look at the distance traveled, so for average speed, we need to know distance traveled over time. Okay, so the distance traveled, if we went from this spot to this spot, we could do that easily by subtraction. So 30.5 minus 50, that's going to give us a negative 19.5. But if you recall, distance has no direction. Distance has no direction. Therefore, delta D is just simply 19.5. So it's weird. I'm figuring out the total distance, but in order to do that, I have to take a subtraction here to figure out how far I went. So 19.5 meters divided by my 3.00 seconds. So yeah, when we figure that out, so 9.5 meters divided by 3 seconds, we get 6.50 meters per second. And no direction because it is speed. It's simply distance over time. When we're looking at average velocity, though, even though the formula looks the same, it's calculated slightly different. So here we're looking at displacement. Now we could use the same thing here, and we got our negative 19, so we will actually use negative 19 because it is the difference between initial and final position. The time period is the same, and we do get 6.50 meters per second here, but we have that negative there indicating that we're going in the negative direction.